Hi, I am Brian Esparza, and I'm doing the Chemistry Edpuzzle project. Now, these are the symbols for alpha, beta, and gamma. For alpha, it's pretty simple, it has an A, same for beta, and the gamma is a Y. How to identify them? I have a little drawing here. It resembles how alpha radiation is easily stopped, it's even stopped by paper. Beta radiation is a bit harder to stop, but it can be stopped by foil paper, and it can penetrate paper. Gamma is the strongest one out of all of them. It can go through paper and foil, but it cannot go through harder stuff like lead. Alpha. A real life example of alpha is in smoke detectors. Like we established, alpha can be stopped by paper and skin, so it can't really be used for too many things, and it is positively charged. Beta. Beta is negative, has a negative charge. It can penetrate paper and skin, and it can penetrate up to half a centimeter into aluminum foil. A real life example is that in industries, it is used to determine how thick a material is, such as paper or plastic. Gamma. Gamma is transmitted through waves. It can penetrate skins and bones and aluminum foil, but it can be stopped by harder stuff like lead or concrete. The gamma rays are not a particle, it is just pure energy and it has no charge or mass. They are used as X-rays to look inside of bodies for medical reasons, and they can help treat cancer. Target 2. Alpha decay. What happens? So, this is a nucleus from an alpha decay. The gray circles are neutrons, and the red circles are protons. In order for a nucleus to become more stable, there has to be an alpha decay particle that is emitted. For example, if element Q is a made up element, represents protons and N represents neutrons. At the top, we have atomic mass that is protons plus neutrons, and at the bottom, we just have protons, which is the atomic number. For this problem, we lose two protons, as you can see from the graph, from the drawing, sorry, and we lose two neutrons and two protons, which they add up to -4. So then element Q2 is created. So we put 4 up here because it's -4, and then 2 down here because it's -2. So now we have to find this element that has the atomic mass of 2 and that has the atomic mass of 4 and the atomic number of 2. If we look for it in the periodic table, we can see that it's helium. So then this would be the whole problem. Here's a practice problem. We have Ra and He. In order to find the element, we have to do 202 minus 4, which equals 218, and then 88 minus 2, which equals 86. But what is the element? We have to look for it in the periodic table. And as you can see, it's at the bottom right, which is Rn. And that is the final answer. Now here's a practice problem that you should try. Okay, now beta decay. Here's the picture again of the nucleus with the protons and neutrons. Beta decay emits electrons in order to stable the nucleus. The electron is inside of the neutron. The mass of the electron is so small that 0 best represents it. And the atomic number is negative. -1. Because it emits an electron, the neutron turns into a proton. So, see the change? Neutron to proton. Okay, let's go back to the made-up element Q. Again, protons plus neutrons are at the top, and the protons are at the bottom. And since the element gained one proton, we add one proton to the bottom. But because the element loses one neutron and one proton, the top over here stays the same as proton plus neutron. And since we changed the protons, this creates a whole new element that we'll call Q2. And this is it for beta decay. Now for positron beta decay, which is pretty much the same thing, but the only thing that changes is that it's protons minus 1, and this is not negative, it is positive. Okay, so let's do a practice problem. We have element C, and then we know it's just a regular beta decay because it is not positive. So in order to find this, we have to do 14 minus 14 equals 0. So then we put 14 up here. And then 6 minus what equals negative 1? 6 minus 7 equals negative 1. So then we put negative 7 down there. But we do not know the element yet. So if we look at the periodic table, the element that has 14 and 7 as the atomic number and mass is nitrogen. I don't know why I wrote a 7 there. I meant that to be an N. So here's a practice problem for positron. 23 minus 23 is 0, so then 23 goes on top. And then 12 minus 11 equals plus 1. So then it's 23 and 11. And if we look for it in the periodic table, we find that it's Na. Now here's a practice problem for you. Next, we have gamma decay. Now, for this one, it's the easiest one out of all of them. Gamma decay does not produce any particles, just energy. And it has no mass, it's just energy. So here's an example. For uranium, it's just the same thing. It does not produce any particles or anything. It's just energy. So it's the same thing on both sides, and then plus energy at the end. And that's gamma decay. Okay, target 3. Half-life. Half-life is the amount of time it takes for half of a radioactive sample to decay into something else. For example, if a 100 grams of element Q has a half-life of 10 years, after 10 years there will only be 50 grams of that element left. The other 50 decay to another element. This is a picture showing after 10 years it decays into element J. How to solve half-life equations? There's two ways to do it, logically and with an equation. The equation is y equals a 1/2 to the power of x. X meaning the amount of half-lives, a is the starting amount, and y is the final number of grams. So let's try to solve this one. The half-life of ZN71 is 2.4 minutes. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes? So before we start plugging in the equation, we have to find the amount of half-lives. So we do 7.2 divided by 2.4, which gives us 3. So we plug in 3 for the amount of half-lives. Then we look at the beginning grams, which is 100, and we plug it in for A. and then we just solve. 0.5 to the power of 3 is 0.125, and then 100 times 0.125 is 12.5, which means y equals 12.5. So the answer to this is 12.5 grams remain after 7.2 minutes. So now you try solving with an equation. Okay, next we have how to solve half-life equations using logical thinking. Logically, just keep subtracting by half until you get the desired amount. For example, if there's 100 grams and you're finding 3 half-lives, it would be 100 divided by 2, then 50 divided by 2, and then 25 divided by 2, which is 3 half-lives, and that gives you the answer. Okay, so let's try to solve this problem logically. We start with a 10 gram sample. We divide it by 2, then we divide 5 by 2, and then we divide 2.5 by 2. That's 3 half-lives, and then the final amount is 1.25. So 1.25 grams remain. But the question is asking how many grams of a 10-gram sample would have decayed after exactly 3 half-lives. So it's how much would have decayed, not how much is remaining. So we do 10 minus 1.25, which equals 8.75 grams decay, and that's the answer. Now you try solving half-life logically. Okay, last target. Target 4. Nuclear fusion and fission. For nuclear fission, it's splitting the atom. It powers nuclear power plants and some nuclear bombs. This is an example of what happens. There's an atom that is unstable. It splits into 2 other atoms that are slightly more stable, and it releases energy. Although these 2 are still kind of unstable, they are more stable than the original. How it works. Here it is again, just the neutrons and the protons. A neutron is launched into a nucleus, then it becomes more unstable. Once it's super unstable, it splits into other nuclei called daughter products. These are more stable than the original, and as they split, it releases energy, and 3 neutrons are created. And then this causes a chain reaction that just keeps going on, and every time they split, it creates more energy. Nuclear fission is used for power plants, bombs, and it's hard to control and contain, but it is controlled and contained. Nuclear fusion. Nuclear fusion requires a temperature greater than 40 million Celsius. It is produced by the sun and stars. It is what powers the hydrogen bomb. How it works. So you have 2 nuclei that combine to form a heavier nucleus. Here are the differences between fusion and fission. Fission creates a lot more waste than fusion. It provides nuclear energy. It is hard to contain, but it is containable. And the heavier nuclei split to form lighter nuclei, producing a chain reaction energy. For fusion releases 3.5 times more energy than fission per unit. It has way less waste, but it is harder to contain the energy. Stars and hydrogen bombs are used with fusion. For fusion, the lighter nuclei combine to form a heavier nuclei. So in conclusion, fission is easier to use for nuclear power plants and for humans to harvest power from. But fusion is just untamable energy that is way stronger than fission. And that is it. Thank you. Hope you enjoyed. And I hope I get a good grade. Goodbye.